Welcome back. Let's learn about gradient vectors. Alright, so previously we learned how to find the derivative or slope in any direction at a point on a surface using a directional derivative defined with the following formula. The derivative in the direction of a unit vector u with components of u1 and u2 for a surface defined by the multivariable function f of xy is equal to the partial derivative of that function with respect to x times the x component of the unit vector plus the partial derivative of the function with respect to y multiplied by the y component of the unit vector. Okay, so this formula should look familiar. This is how we have calculated directional derivatives so far, but there's actually something interesting about this formula that we really haven't talked about yet. Notice that in these two terms, we have the partial derivative with respect to x multiplied by the x component of the unit vector, plus the partial derivative with respect to y times the y component of the unit vector. The x's and the y's match up in this formula. And so as a result, this calculation is reminiscent of something that we have calculated earlier in Calculus 3. And what I'm referring to here is the dot product between two vectors, right? Remember that the dot product between two vectors, v and u, looks like this. You take the x component of vector v times the x component of vector u and add that to the y component of vector v times the y component of vector u. And if these were three-dimensional vectors, there would be another term where you add the product of the z components. Okay, but altogether, the dot product of two vectors is equal to the sum of the products of corresponding components. That can be directly compared to our formula here for a directional derivative. We could view this calculation as a dot product between two vectors. One of those vectors is pretty clear, right? Obviously, we're working with a unit vector u that has components of u1 and u2, but the other vector here would have to have components of these partial derivatives. And so we could do that. We could define a vector whose x component is fx and y component is fy, and then take the dot product of that vector with the unit vector, and you would get the same exact calculation here that we use to find a directional derivative. Okay, and so here's what that would look like. We would have a vector with an x component of fx, so we have fx times I, plus a y component of fy, and that's multiplied by j. So we'll take that vector and dot product it with the unit vector u, which has components of u1, so we have u1 times I, plus the y component of u2, and so that's multiplied by j. All right, we have the dot product of two vectors here, and so the result of that would be the sum of the products of their corresponding components. So multiply the x components together, fx times u1 gives you the first term, then you add that to the product of the y components, fy and u2, to get the second term. Okay, and so a dot product here makes sense. This is a completely valid way of defining a directional derivative. And it makes even more sense when you consider the result of a directional derivative, right? The directional derivative produces a value of slope, which is a scalar quantity, right? It's not a vector, just like how the dot product produces a scalar quantity. It does not result in a vector. But there's actually a bigger takeaway here than just redefining the directional derivative with a dot product, and it has to do with this vector right here. This new vector that we have created where the components are the first partial derivatives of a multivariable function. This is actually a very important and useful vector for Calculus 3, and it has a special name of the gradient. We call this vector here the gradient vector, and it also has a special notation. It's represented by this. You want to draw an upside down triangle, or really it's an upside down delta, right? The Greek letter delta. If you flip it upside down or invert it, this is what it would look like. You use that symbol followed by f of xy, and that right there represents the gradient of a multivariable function f of xy. Okay, you can sort of think of this symbol as an operator that when used on a function produces a vector, specifically a vector with an x component that is the partial derivative with respect to x and a y component that is the partial derivative with respect to y. Okay, and so you could read this as the gradient of f of xy, or the gradient of f, or sometimes you might also hear this pronounced as just del f, spelled out del, but most of the time I'm just going to call this the gradient of a function. Okay, but with the help of this gradient vector, we now have a new and slightly better way to find a directional derivative, right? We can now say that the derivative in the direction of a unit vector u for a multivariable function f of xy is equal to the dot product between the gradient vector for that function and the unit vector. Okay, this is our new formula for finding a directional derivative. And so to summarize what we've talked about so far, the gradient for functions of two independent variables is defined like this. For a multivariable function, z is equal to f of xy, the gradient vector, is represented by this notation, del f of xy, and that's equal to a vector with an x component of the partial derivative with respect to x and a y component of the partial derivative with respect to y. And then using this gradient vector, we now have an alternate form of the directional derivative, specifically the derivative of a function f of xy in the direction of a unit vector, can be found by taking the dot product between the gradient vector and that unit vector u. Okay, and so now that you've been introduced to the gradient vector, as well as this new way of finding a directional derivative, let's take a look at a quick example where we will find a directional derivative with the help of the gradient vector. For this example, we want to find the directional derivative at point P with coordinates of 1, 1 in the direction of vector v. And we're given f of xy is equal to negative x squared minus y squared plus 9. And vector v is equal to 4i minus 3j. Okay, so what we're going to do here is find this directional derivative using our new formula that the derivative in the direction of a unit vector u for this function f of xy is equal to the dot product between the gradient vector del f of xy with the unit vector u. All right, and so if we specifically want to find the directional derivative at point P with coordinates of 1, 1, then really what we want to find here is the derivative in the direction of u of f of 1, 1, which will be equal to the gradient vector evaluated at 1, 1. And then, of course, you'll take the dot product of that with the unit vector. Okay, so let's work on finding these different pieces. And let's start with the gradient vector. We know that the gradient vector for f of xy is equal to the partial derivative with respect to x as the x component, and then the partial derivative with respect to y as the y component. Okay, so let's find the partial derivative with respect to x. Looking at our multivariable function here, negative y squared and 9 would both be constants with respect to x, so their derivatives are 0. And then negative x squared, its derivative is negative 2x. So this is equal to negative 2x times I plus the partial derivative with respect to y. And so looking at this function, negative x squared and 9 would both be constants with respect to y. Their derivatives are 0. But negative y squared, its derivative, would be negative 2y. So what we'll have here is negative 2xi minus 2y times j. Okay, so that would be the gradient vector in terms of x and y. But remember that in order to find this specific directional derivative, we do want the gradient vector evaluated at 1, 1. So let's find that here. We want to plug in 1 and 1 for x and y in the gradient. So that will be equal to negative 2 times 1 times I minus 2 times 1 times j. So we get negative 2i minus 2j. Okay, so that's the gradient vector evaluated at 1, 1. And so that's half of what we need here to find this directional derivative, but we still need the unit vector, which will be based on the vector that we've been given here. We want to find the directional derivative in the direction of this vector, but we can't just use this vector as it is. We need to first check to see if it's a unit vector, and if it is, then of course we can use it in this dot product right away, but if it's not, then we need to turn it into a unit vector. Okay, so remember, a unit vector is equal to a vector divided by its magnitude. And so let's see what the magnitude of vector v is here. The magnitude of vector v will be equal to the square root of the sum of the components squared. So we have 4 squared plus negative 3 squared. 4 squared is 16, negative 3 squared is 9, so 16 plus 9 is 25. So what you get here is a square root of 25, which is 5. All right, so the magnitude of that vector is not 1, so it is not a unit vector, but we can very quickly turn it into a unit vector by dividing both of those components by the vector's magnitude, which is 5. Okay, so the unit vector here will be equal to 4 divided by 5, or 4/5 times I, minus 3 divided by 5, or minus 3/5 times j. Okay, I just took vector v, which is 4i minus 3j, and divided it by its magnitude, which is 5. So now instead of 4i and minus 3j, we have 4/5 I and minus 3/5 j. And so now we have everything we need to find this directional derivative. We now have both the gradient at 1, 1 and the unit vector. So now we can take the dot product of those two vectors, which will just be equal to the sum of the product of corresponding components. So we'll start by multiplying the x components. We'll have negative 2 times 4/5. So write that down, negative 2 times 4/5 plus the product of the y components. So you'll have negative 2 times negative 3/5. So we have negative 2 times negative 3/5. All right, and so then simplifying, we get negative 8/5 plus 6/5. And then negative 8/5 plus 6/5 is equal to negative 2/5. And that right there is the final answer. That is the directional derivative, or the slope, at this point on this surface in the direction of this vector, or more specifically, this unit vector down here. Okay, that slope is negative 2/5. And this would be the same exact answer that you would have gotten in the past if you used our original formula for a directional derivative, because the calculation is exactly the same. We're just representing it a different way using a dot product. Okay, this calculation right here is still fx times u1 plus fy times u2. It's just being expressed in a different way. And depending on the scenario, it is a more convenient and easier way to go about a directional derivative. Okay, so this is one use of the gradient vector. We can use a gradient vector to find a directional derivative, but what else could we do with it? Or what does it actually represent? Well, that's what I want to take a look at next. What we're going to do is discuss and go over the properties of the gradient vector, and I want to begin by just filling in some of the basic details around the gradient vector, and then we'll go a little bit deeper into its actual properties. And by the end, you'll have a full picture of what the gradient vector is and what it does. And so to start, it's important to realize that a directional derivative is a scalar quantity, right? It's just a number. It represents the slope at a point on a surface in a particular direction. But that direction is described by the unit vector, not the slope value itself. So it's just a scalar quantity, while the gradient vector is a vector quantity, right? When we found the gradient in the example just a little bit ago, what we found was a vector with an x and y component. Those two components form a vector quantity that have both a magnitude and a direction. Okay, so it's very important that you understand that difference. But then as a little bit of an introduction to what the gradient vector actually does, or what it represents, the gradient vector relates the grade or the steepness of a surface relative to the horizontal, or the xy plane. Okay, so we're going to talk about this in more detail in just a little bit, but for right now, you just want to know that the gradient vector is going to help describe the steepness of a surface at a particular point when compared to the xy plane. All right, and then finally, the last very basic idea that I want you to keep in mind is that the gradient is always one dimension lower than the function you have the gradient of. Okay, and you can see that in our example that we just did. If we were to take a look at the graph of the surface that we were working with, it looks a little bit like this. Our function f of xy was equal to negative x squared minus y squared plus 9, which is an elliptic paraboloid. And we are specifically looking at the directional derivative at this point on that surface, the point with coordinates of 1, 1, and then the z coordinate would be 7. And we found the slope at that point in a particular direction. But during that process, we found the gradient vector for that point. We have the gradient of f of 1, 1, which was equal to a vector with components of negative 2, negative 2. Okay, so the function f of xy represents a three-dimensional surface, while the gradient is a two-dimensional vector. And so if we were to plot this or graph it in this 3D coordinate system, that vector would be contained within the xy plane. All right, technically the z component here would be 0, so the gradient vector would just be contained within a plane, that being the xy plane. It is technically not a vector in 3D space in this scenario. And if we wanted to actually graph or plot this vector in the xy plane, what we would want to do is have its initial point at the point 1, 1. I guess technically you could plot it with its initial point at the origin, but since we're working with a specific point here, I think it makes a little bit more sense to relate it to that point. And so this point on the surface has x and y coordinates of 1, 1. And so if you make that z coordinate 0, that point would be located somewhere right about here in the xy plane. That would be the point 1, 1. From that point, you could draw this gradient vector. Its x component is -2, and its y component is -2. So from this point, to find the terminal point, you would move -2 in the x direction and -2 in the y direction. All right, so I'll say that that point is somewhere out here. This is not going to be a perfect graph here. I'm just sketching this gradient vector, but that vector would look something like this. Okay, again, not a perfect drawing, but you get the idea. The gradient vector here is a 2D vector contained within the xy plane pointing in this particular direction. But how does that vector and its direction relate to the steepness or the grade of this surface at this point? Right, I told you that the gradient relates the grade or steepness of a surface relative to the horizontal or the xy plane. But what does that actually mean? Well, in order to understand that or to make that more clear, we need to go over the actual properties of the gradient. Okay, so far I've just gone over some of the basics, but now we want to actually look at the properties of the gradient vector. And for all these properties, we're going to be working with these different pieces of information. We'll have a multivariable function, z is equal to f of xy, a unit vector, u, and a scalar value c. And so the first property is that if the gradient vector for that function is equal to the 0 vector, meaning that both of its components are 0, then the directional derivative for that function is equal to 0 for any unit vector. It doesn't matter what the unit vector is. If the gradient vector is a 0 vector, the directional derivative, or the slope, will always be 0. And that should make sense if you think back to the alternative formula for the directional derivative that we found in this video. It's the dot product between the gradient vector and the unit vector. And so if the gradient vector is 0, when you calculate that dot product, you're multiplying a component of 0 by both of the x and y components of the unit vector. All right, so you'll have 0 times u1 plus 0 times u2, which will just be 0 because anything times 0 is 0. All right, so this will always be true. If the gradient vector is a 0 vector, it doesn't matter what unit vector you're working with, the directional derivative will be 0. But then for the second property, the directional derivative for f of xy has a maximum value of the magnitude of the gradient vector, which occurs when the unit vector is equal to a scalar multiplied by the gradient vector. Or in other words, when the unit vector is parallel to the gradient vector, right? If the unit vector is equal to a scalar multiplied by the gradient vector, what that's saying is that those two vectors are scalar multiples, and we know that vectors that are scalar multiples are parallel vectors. So if u is equal to some scalar times the gradient vector, then the unit vector and the gradient vector are parallel. Okay, and when that is the case, when those two vectors are parallel, because they won't always be, but when they are, that is where the directional derivative has a maximum value. Specifically, that maximum value will be the magnitude of the gradient vector. And this is an important property. In fact, it's so important that I want to show you why it's true, because that will give us even more insight into what the gradient vector is and what it represents. And so as a little side proof here, we're going to informally prove that this second property is true. And what we'll start with is the alternative formula that we found for calculating a directional derivative. Remember that the derivative in the direction of u for a function f of xy is equal to the dot product between the gradient vector and the unit vector. And then what we'll do is rewrite this dot product with a formula that we learned about earlier in Calculus 3. Specifically, this is the formula I'm referring to. Remember that the dot product between two vectors, so let's say we have the dot product between a vector v and a vector u. Another way that you could calculate that is by taking the magnitude of vector v times the magnitude of vector u, and then multiply that by cosine of theta, where theta is the angle between those two vectors. Okay, so applying this formula to this dot product, we can also say that the directional derivative is equal to the magnitude of the gradient vector. So we have del f of xy, and then you multiply that by the magnitude of u, the unit vector, and then you multiply that by cosine of theta, the angle between those two vectors. Okay, but remember, u is a unit vector, which by definition means that its magnitude is 1. So this can be eliminated. The value of that magnitude is just 1. So we get that the directional derivative is equal to the magnitude of the gradient vector So we have del f of xy, and that will be multiplied by cosine of theta, where again, theta is the angle between those two vectors. And so this right here is another way of calculating a directional derivative, but in this form, we can analyze the maximum value of this directional derivative. Because remember, cosine has a maximum value of 1, right? You could plug in whatever angle you like into the cosine function, but it will never output a value bigger than 1, right? 1 is the maximum value that it produces. And you could see that graphically. If you graphed cosine in the xy plane, it looks something like this. The highest y value it reaches up to is positive 1. And in the same way, the lowest y value it reaches to is negative 1, which we'll get to that in just a second, but for now, just focus on the maximum value, or the maximum output for cosine, and that is a value of 1. And that maximum value of 1 occurs when the angle is 0, right? You can even see that on the graph here. When x equals 0, which in this case we're viewing as theta, when that value is 0, the y value is 1. Now, yes, that occurs again and again forever, but remember, we're talking about the angle between these two vectors, so that is limited to be between 0 and pi, because if you're looking at two vectors, let's say like this, you're always going to measure the smallest angle between them. And so while you could have an angle that's bigger than pi, you can measure this angle here. Usually we don't do that. We refer to the angle between two vectors as being this angle right here. And so the biggest that that could ever be is pi if those two vectors are pointing in opposite directions. And then of course the smallest that that angle could be is 0 if they are pointing in the same direction. And so hopefully some different light bulbs are turning on for you here, because now if we put everything together, what's going on here is we know that the maximum value of cosine is 1, which happens at an angle of 0. And if you have an angle of 0 between your two vectors, then those vectors must be parallel. They must be pointing in the same direction, all right? For any other angle that you plug into the cosine function, you'll get a value that is smaller than 1. And so when you multiply any of those values smaller than 1 by the magnitude of the gradient vector, you'll be taking a fractional amount or a piece of that magnitude, and so that wouldn't be the maximum value. The maximum value only occurs when cosine is 1 at theta equals 0, which means you'd have 1 times this magnitude, giving you that the maximum value for the directional derivative is the magnitude of the gradient vector, which again only occurs when the angle between the two vectors is 0, or in other words, when the unit vector and the gradient vector are parallel, when they're pointing in the same direction. And so that's the proof behind this second property. But from this proof, we can also support the third property, which has to do with the minimum value of the directional derivative, right? Remember that we talked about how cosine has a maximum value of 1, but it also has a minimum value of negative 1. Cosine will never output a value smaller than negative 1. So the smallest value that you could get here is negative 1. So you'd have negative 1 times this magnitude. So the negative magnitude of the gradient vector would be the minimum value for the directional derivative, and that will occur when the angle between the two vectors is pi, right? Cosine of pi is negative 1. That gives you that minimum value, and when the angle between two vectors is pi, they're still parallel, but now they would be pointing in opposite directions, right? It could look something like this. One vector is pointing this way, and the other vector is pointing this way. The angle between them is pi, or 180 degrees. That is where cosine is negative 1, which would produce the minimum value for the directional derivative. For any other angle that you plug into cosine, you will get a bigger value than negative 1, and so you'd be multiplying that by this magnitude, which would give you a value that is bigger than the minimum value of the negative magnitude of the gradient vector. Okay, so if we write that out, the third property of the gradient is this. The directional derivative has a minimum value of the negative magnitude of the gradient vector, which occurs when theta equals pi. Or in other words, the unit vector and the gradient are parallel, but they point in opposite directions. Okay, so in both cases, the directional derivative has a maximum value and a minimum value when the unit vector and the gradient vector are parallel, but it depends on whether they are pointing in the same direction or the opposite direction if that value is the maximum or the minimum. Okay, so those are the three properties of the gradient that I wanted to cover here. But before we move on, the second property of the gradient here, if we think about it a little bit deeper, gives us a way better idea of what the gradient vector actually does, or what it represents, right? Because if the directional derivative has a maximum value of the magnitude of the gradient vector when that vector is parallel to the unit vector, then what that means is that the gradient gives the vector for the steepest grade of a surface at a point. And let me explain. Remember that a directional derivative represents the slope at a point on a surface in a particular direction. And so that means that its maximum value would be the largest slope possible, or the steepest slope at that point. And so if that maximum value of slope, or if that steepest slope occurs when the gradient vector is parallel to the unit vector, then that means that the gradient vector points to the direction of the steepest slope of the surface at a point. All right, you can maximize the value of the directional derivative at a point by making sure the unit vector is pointing in the same direction, or it's parallel to the gradient vector. And so let me show you what I mean by that visually. If we go back to our graph from earlier that was based on our example problem, notice the direction that the gradient vector is pointing towards. It's pointing in a direction towards negative x and negative y values, or you could think of it as pointing in the direction of the third quadrant of the xy plane. But regardless, that vector is pointing in the direction where this surface would have the steepest slope at this point. It's not the easiest thing to visualize here, but remember that this surface is an elliptic paraboloid, specifically one that is upside down. So think of it as a bowl that is upside down. It would make sense that at this point, this direction, which is the same direction as this gradient vector, is the direction where this surface would have the steepest slope at this point. Okay, you could draw a tangent line at that point in that direction, and that tangent line would have the steepest possible slope that you could have at that point on this surface. The gradient vector gives you the direction such that that is the case. So that means when you find a directional derivative at this point on this surface, if the unit vector that you're using for the direction of that directional derivative is parallel or has the same direction as the gradient vector, you will find the directional derivative that has the steepest slope for the surface at that point, which in our scenario here would be this slope. Okay, so for that directional derivative, if you use any unit vector that is not parallel to the gradient, then you could think of that unit vector as turning away from the gradient vector, which means it's turning away from the direction of the steepest slope. Okay, so if you draw a tangent line at that point in any other direction, the slope of that tangent line will be a smaller slope than the slope of this tangent line that's in the direction of the gradient vector. And in the same line of thinking, the opposite direction of the gradient vector, which would be this direction, would be the direction of the smallest slope, or the least steep slope. Okay, numerically, it's the same as the steepest slope, but it's just negative. And so that's the big picture. That is what the gradient vector represents. It's related to the grade, or the steepness, of a surface relative to the horizontal, or the xy plane, or more specifically, it's a vector that will point in the direction of the steepest grade, or the steepest slope of a surface at a point. But now that's everything you need to know regarding the gradient vector when working with multivariable functions of two independent variables. And so let's take a look at an example problem where we will use the gradient vector. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so for this example, we want to find the gradient at the point 2, 3 and use it to find the maximum value of increase and decrease at that point for the function. Or another way that you could read this is that you want to use the gradient to find the maximum value and the minimum value of the slope at this point on the function. All right, and the function that we're working with here is the multivariable function f of xy is equal to the natural log of x squared minus y. Okay, so to do anything here, we do have to first find the gradient, and remember that the gradient vector, del f of xy, is equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j. Okay, so let's start by finding fx. What would be the partial derivative with respect to x of this multivariable function? Well, we have an expression involving x inside the natural log function, so we do need to take the derivative of that natural log function, which will be 1 divided by the inside function multiplied by the derivative of that inside function. Okay, so we will have 1 divided by x squared minus y times the derivative of x squared minus y. And the derivative of x squared is 2x, and negative y is a constant with respect to x, so its derivative is 0. So we're just multiplying by 2x. Okay, so that's fx, and that's multiplied by I, and then we'll add that to fy. So let's take a partial derivative of this function with respect to y. Once again, we do need to take the derivative of the natural log function because there is an expression involving y inside of it. So we're still going to have 1 divided by that inside function of x squared minus y, but then the derivative of the inside function is not 2x this time around because x squared with respect to y is a constant. Its derivative is 0, but then negative y, its derivative would be negative 1. So we're multiplying by negative 1, and then that would be multiplied by j. Okay, so that would be the general gradient vector in terms of x and y, but remember we do want to find the specific gradient at the point 2, 3. So what I'll do is plug 2 and 3 in for x and y in the gradient and then simplify all at the same time. Okay, so here's what we'll get. We'll have the gradient vector evaluated at 2, 3, and that will be equal to 1 divided by x squared. So we have 2 squared minus y, which is 3, times 2x, so we have 2 times 2, times I, plus 1 divided by 2 squared minus 3 times negative 1. So I'll just multiply that into the numerator, which will make this whole term negative. So I'll erase this plus sign and make it negative and multiply by j. Okay, and then simplifying, 2 squared is 4, minus 3 is 1. So we have 1 divided by 1, which is 1, times 2, which is 4. So we get 4i. And then for j, 2 squared is 4, minus 3 is 1, 1 divided by 1 is 1, so we have minus 1j, or just minus j. Okay, and that right there would be the gradient vector at the point 2, 3 for this multivariable function. And remember what this represents. It's not slope, it is not a directional derivative. Instead, this gradient vector is the vector that gives us the direction that the tangent line would need to have the maximum slope for this surface at this point. Okay, so this vector is pointing in the direction of the maximum slope for this surface at that point. And if you wanted to, you could take this gradient vector and dot product it with any unit vector you like, and you'd be able to find the directional derivative or the slope in the direction of that unit vector at that point on the surface. But that's not what we have to do here in this example. Instead, we want to use that gradient vector to find the maximum and minimum values for the directional derivative at that point. Okay, I'm rephrasing this here. That means the same thing as the max value of increase or decrease at that point. The increase/decrease refers to the maximum and minimum slope. Okay, so let's start with the maximum. Remember that the maximum slope will be the magnitude of the gradient vector. So we'll take the magnitude of del f of 2, 3. And then for the minimum slope, or the max value of decrease, we want the negative magnitude of the gradient vector. So the negative magnitude of del f of 2, 3. Okay? And so let's calculate that magnitude. Remember that the magnitude of a vector is just equal to the square root of the sum of its components squared. So this will be equal to the square root of 4 squared plus negative 1 squared. And 4 squared is 16, negative 1 squared is 1. So 16 plus 1 is 17, giving us that the magnitude is the square root of 17. That value, which is approximately 4.123 and some more decimals, that's about what the square root of 17 is, that value would be the maximum slope or the steepest slope for this function at this point. And then the minimum slope would just be the negative version of that magnitude So the minimum value, or you could view it as the maximum value of decrease, is the negative square root of 17. Okay, so those are the two answers we were looking for in this example. Now, just like many other concepts in Calculus 3, we can extend the gradient as well as directional derivatives for multivariable functions of more than two independent variables. You can extend the gradient to functions of 3 variables, 4 variables, 5 variables, and so on, and then use those extended gradients to help you find directional derivatives of those functions as well. But right here in this video, I'm just going to highlight the extension to functions of 3 independent variables, and I think from there, extending to functions of more independent variables is fairly intuitive, and you'll see what I mean. And so to start, here's what the gradient vector would look like for a function of 3 independent variables. If you have a function w is equal to f of xyz, which would represent a 4-dimensional shape of some kind, you can find the gradient vector for that function. The gradient vector del f of xyz is equal to fxi plus fyj plus fzk. Or in other words, the partial derivative with respect to x is the x component, the partial derivative with respect to y is the y component, and the partial derivative with respect to z is the z component, and that vector is a 3-dimensional vector. So notice here that just like for multivariable functions of 2 independent variables, the gradient vector is 1 dimension lower than the actual function that it is the gradient vector of. Okay, the function itself represents a 4-dimensional shape, but the gradient vector is a 3D vector. It is 1 dimension less, so that still holds true. Really, the only difference between this gradient vector and what we've worked with before is that there is an additional z component, and that z component is the partial derivative of the function with respect to z, that third independent variable. Okay, so if you had a function of 4 independent variables, you would add another term or another component that would involve the partial derivative with respect to that fourth independent variable, and then of course it would be multiplied by whatever standard unit vector that you would use for that fourth dimension. All right, so that's how you would extend for more independent variables. But then using this gradient vector for a multivariable function of 3 independent variables, we can now find directional derivatives for these functions of 3 independent variables. This is something that we did not look at in the previous lesson on directional derivatives. In fact, I believe I told you that we would extend the concept to more variables later on, which is what we're doing right now. The directional derivative, or the derivative in the direction of a unit vector for that function f of xyz, is equal to the dot product between that gradient vector and the unit vector, where that unit vector is now defined as a 3-dimensional unit vector. So it has components of u1, u2, and u3, u3 being the z component. And so if you perform that dot product, you will get the formula of fx times u1 plus fy times u2 plus fz times u3. Okay, so the formula is not all that different from directional derivatives for functions of 2 independent variables. You just have that extra term involving the z components of the gradient vector and the unit vector. Okay, and as you can imagine, if you have a multivariable function of more independent variables, you can continue to add on more terms, where you multiply those fourth components and so on from the vectors and add them to these other terms. Okay, it's pretty rare that you'll ever do that. Usually you just work with either 2 or 3 independent variables within this course, but it is possible to go beyond that. And one final note about this extension of the gradient vector: all the properties that we looked at earlier for the gradient of f of xy can be extended to the gradient of f of xyz. And what I mean by that is the maximum value of a directional derivative is still the magnitude of the gradient vector, and the minimum value is still the negative magnitude of that gradient vector. And if that gradient vector is equal to the 0 vector, meaning that if all of these components are 0, then very clearly the directional derivative would also be 0 no matter what unit vector you're using. Because if all of these components are 0, then you have 0 times u1 plus 0 times u2 plus 0 times u3. All those terms would be 0, and so the whole directional derivative is 0 no matter what those values of u1, u2, and u3 are. Okay, so those 3 properties that we looked at earlier still apply here, and for all gradient vectors you may work with. All right, and so with that, let's close out this lesson by looking at one more example problem where we are given a multivariable function of 3 independent variables. And so here is our example. We want to find the gradient and directional derivative at the point 3, negative 1, 1 in the direction of vector v. And we're given the multivariable function f of x, y, z is equal to x squared plus 2y squared minus 4z. And the vector that we've been given, vector v, has components of 2, negative 4, and 4. Okay, so this is very similar to problems that we have done in the past. The only difference is that we're working with an extra dimension. And so let's just get right to it here. We know that the derivative in the direction of a unit vector u for this multivariable function, f of x, y, z, will be equal to the dot product between the gradient vector, del f of x, y, z, with the unit vector, vector u. And in this case, we do want a specific gradient and directional derivative. We want it at this point of 3, negative 1, 1. And so let's write that out as well. We want to find the derivative in the direction of u for f of 3, negative 1, 1. And that will be equal to del f of 3, negative 1, 1 dot product with vector u. Okay, so let's work on this. Let's start by finding the gradient vector. Del f of x, y, z will be equal to fx times I plus fy times j plus fz times k. All right, and so let's start with fx. Looking at our function here, these two terms are not in terms of x, so they are constants whose derivatives are 0, but then x squared, its derivative is 2x. So the gradient is equal to 2x times I plus fy, so now we're taking a partial with respect to y, and looking at these terms, x squared and negative 4z are not in terms of y, their derivatives will be 0, and then 2y squared, that derivative would be 4y. So we're adding 4y multiplied by j, and then we want to take the partial derivative with respect to z. We want to find fz for this function. And so x squared and 2y squared are not in terms of z, they are just constants whose derivatives are 0. And then negative 4z, the derivative of that with respect to z would be negative 4. So instead of plus, we will have minus 4 times k. All right, and so that is the general gradient vector, but we do want to use the specific gradient vector at this point. So let's plug in those values of x, y, and z. We'll have del f of 3, negative 1, 1. And that will be equal to 2 times x, where x is 3, so 2 times 3 is 6. So we have 6i plus 4y, where y is negative 1, so 4 times negative 1 is negative 4. So instead of plus, we will have minus 4j. And then the last term is just negative 4k, so there's nothing to plug in there. I'll just write down minus 4k. So that's half of what we needed. We now have the gradient vector at that specific point, but we do need to dot product it with the unit vector for this scenario, which we currently don't have, at least I don't think so. We are given a vector that we want to find the directional derivative in the direction of, but we don't know if that's a unit vector or not, so we do want to check that. We want to calculate the magnitude of that vector. If it's 1, then it's a unit vector, and we can use its components as they are in this dot product. But if the magnitude is not 1, then we want to divide that vector by its magnitude, and that will give us the unit vector that we want. Okay, so let's calculate the magnitude. The magnitude of vector v will be equal to the square root of the sum of the components squared, and there are 3 of them. We have 2 squared plus negative 4 squared plus 4 squared. And so 2 squared is 4, negative 4 squared is 16, and 4 squared is 16. So we have 4 plus 16, which is 20, plus 16, which is 36. So we get the square root of 36, which is 6. And so the magnitude is a nice number, but it's not 1, so this vector is not a unit vector. But if we divide all of those components by that magnitude of 6, then we will have a unit vector. Okay, once again, remember that a unit vector is equal to a vector divided by its magnitude. And so that's what we're going to do here. The unit vector that we want to use will be equal to each of these components of this vector divided by 6. And I'm just going to keep that on the outside. And here's what I mean by that. I'm just going to write 1 divided by 6 multiplied by 2i minus 4j plus 4k. Okay? Those are the 3 components of this vector. I'm just writing it out using the standard unit vectors instead. And then dividing all those components by 6 would be the same as multiplying all of them by 1/6. Now here's the reason why I did this, why I'm keeping that 1/6 on the outside, is because it will keep these components nice for our dot product. Okay, otherwise we will have some fractions to work with. But if we keep this scalar out front, remember that for a dot product, you can pull out a scalar from either of the vectors to the front of that dot product and just multiply it by the result of the dot product. Okay, so what I mean by that is we can take the dot product of the gradient vector with this vector and just multiply it by 1/6. And that would be the same thing as if we did multiply 1/6 by all these components and then took the dot product of those two vectors. Okay, so this directional derivative will be equal to that 1/6 multiplied by the dot product of the gradient vector with this vector. So ignore that 1/6 because we're going to be multiplying it by the result of the dot product. So we'll take the sum of the product of corresponding components. Starting with the x components, we have 6 times 2, which is 12. And then we'll add that to the product of the y components. So we have -4 times -4, which is positive 16. So we have 16 plus the product of the z components. So we have -4 times +4, which is -16. So instead of plus, I'm going to write minus 16. And that's our dot product calculation. But then notice that we have positive 16 and -16. Those will cancel out to be 0. So we just have 1/6 times 12, which is 2. And so that would be our final answer. The directional derivative at the point 3, -1, 1 in the direction of this vector is 2. And to find that, we did use the gradient at that point, which was this vector right here. So I'll box that in as well because we also wanted to find that for this problem. But those two answers are the final answers to this example. We have now found both the gradient at this point on the function and the directional derivative at that point in the direction of v. Okay, and so with that, that is it for this lesson. But if you do want to get some more practice finding and working with gradient vectors, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.